Good day, I'm Shion Adekunle, and today I want to talk to you about developing a smart outlet system and its various components. To introduce myself, I'm a freshman major in computer science. I started working on this project my junior year of high school, so I initially worked on adding to the progress made by previous members. So initially, I didn't know what to do or what technical stack to pick when completing this project. But my team members were helpful in providing the background knowledge that I needed to learn about this project and the scope. They pointed me to some papers I should read, and they also pointed me to some technology tools I should learn in order to make progress on this project. And so the lab, the University of Kentucky College of Computer Science, was very helpful in helping me get started. So I worked on adding to the progress made by previous members. So I worked on developing the server, on developing the Android app, and later on during the course of the project, other members also worked on added to my progress and added more features than what I did. So I would then go into describing an overview of the system. So there are three basic components to this system. We have a server, an app, and an outlet. But as this system continues to expand, what we'll have is that we'll have multiple outlets. Let's say in an office, in a building, in a room, or even in a city block, all connected to a single server. The server was built using Python, and it hosts a database and the machine learning algorithms. While the app allows the users to control the outlet, turn it on or off, and label the data. The app also has a view that allows users to monitor the data. The Arduino Smart Outlet, it was built on the Arduino platform as the name suggests. So the way the system works is that the data from the outlet, the current from the outlet is transmitted wirelessly to the server. In addition, once the data reaches the server, that data is also transmitted wirelessly to the app so the user can see it. In addition to that, the data that is collected from the outlet will be used to train the machine learning algorithms and also will be stored in the database along with the labels sent from the app by the user. So we have several packets of data all being transferred between the components synchronously at the same time. Uh, so so that's why we call it a system because they all depend on each other for data and to achieve our goal.
Today we're going to be presenting our smart outlet system, which we use for machine learning research. We're able to use the data our device collects to train machine learning models and to classify devices in real time. This has some wide-ranging applications for use in consumer homes, such as fine-grained power tuning and management. Our smart outlet is comprised of several main components. We have an Arduino Uno, we have a Raspberry Pi, we have a 5-volt relay along with the ACS 712 current sensor. The way our outlet operates is we plug in a device here to the plug itself, and then the current that the device draws goes through this wire through our current sensor, which outputs an analog value between 0 and 5 volts. Our Arduino reads that value, converts it to digital, and then sends it over the SPI interface over to our Raspberry Pi. The Raspberry Pi then does further processing on the sensor data, and then it sends it over Ethernet to our computer. The 5-volt relay here is able to turn on and off the device remotely, so we can send commands from a computer or a smartphone to turn off the device. And the reason why we're not able to use the Raspberry Pi directly and why we have to use a Arduino Uno as well is because the Raspberry Pi here does not support analog input. It only supports digital. So we have to use this pretty much as a analog to digital converter for the Raspberry Pi, which we could replace it with a integrated circuit that would also do the same job. The other component of our system is the laptop, and this is used for taking the data that we receive from the Raspberry Pi, putting it in a database for long-term storage, and also for displaying and processing the data further and running machine learning over it. We're going to take a look into the software that we wrote for it in just a minute.
The first program we wrote is the Instantaneous data server. We made it in Python and it listens for a TCP connection from the Raspberry Pi. It's over on the left-hand side of the screen. This server uses the raw values sent to our computer from our current sensor and maps the 0 to 5 volt analog value to a value between -30 and +30 amps. We use this for recording high-frequency data between 30 and 50 Hz. It does not have visualization like our other software, but we're able to look at the minimum and maximum values to see what it's doing. Conventional homes wall power is AC, or alternating current, meaning the power in the wall follows a sinusoidal pattern that oscillates around 60 Hz. Here, because we're sampling at high enough rates, we're able to see the fluctuation in the power, which means the average current will be 0 amps, contrary to what you would think. Our next program operates at a much lower sampling rate, so we have to take a different approach. Our next program uses RMS power, or root mean squared. While the average voltage of wall power is 0 volts, the RMS value is 120, which is more meaningful and is what people usually talk about. We can calculate this value by finding the voltage at a peak, then dividing it by the square root of 2. The image from the electrical engineering stack exchange is a good visualization. The next program we wrote was a full-fledged web server with more functionality. Like the other program, we used Python. However, instead of using TCP connections, everything is done over HTTP. At first, you can see the small fluctuations in resting power, but when we plug in the device, our server tries to classify it immediately. The first several classifications are incorrect, as our device only has a few data points and doesn't have enough information to make an accurate decision. After more data points, it's able to correctly identify the device we connected as a Dell laptop charger of the 65-watt variety. We've trained our classifier with several other devices in our paper, and we're able to classify up to 9 different devices. We are even able to distinguish between similar ones, such as different laptop chargers or different computer monitors. The basis of our machine learning approach is k-nearest neighbors. For a new signature, we look at the most similar ones around it and use them to classify it. The k is how many neighbors to look at, and in this example, we'll be using 3. For example, point 1 has 2 red neighbors and only 1 green, so we group it with a red and classify point 1 as a space heater. For point 2, all 3 neighbors are blue, so we classify it as a laptop charger. To determine the distance in this figure, we can just look at it. However, our computer has to do this programmatically, so we use dynamic time warping to compare the 2 different signatures.
Plug. It is an Android app that allows for remote control of the outlet. And I will then go over to a demo that shows you how this app works. So what we have here is the Android app plug going on a Pixel 4 XL emulator. Like I mentioned earlier, it has a clean and simple design, with a switch and with a button at the top right that allows the user to label the data, which we will see very shortly. There's also a device name at the top to indicate the machine learning prediction. You can see here the screen in which users can label the device plugged into the outlet using previously defined options. They can see what percentage of users picked a certain label on which one they can choose from the list of options. There's also a switch, like I mentioned earlier, that allows the user to control the outlet remotely. And below that, we have the name for the outlet, AR indicating Arduino. At the bottom part of the app, we have the currently running through the outlet shown in amps, and below that, we have a graph that shows the current running through the outlet in real time. So the user turns on the device, and we can see a jump in the graph. The user turns off the device, and we can see a dip in the graph, all in real time. Here you can see the code that controls the entire system. So we'll first go through the code that controls the server. You can see here the code that the file that controls the server data coming in from the Arduino outlet, the data signatures. You can also see the code that communicates with our machine learning algorithms that we define in another Python file. You can also see the main code that references other program files in the server folder. Next, we'll go to the code that controls the Arduino outlet itself. We look at the code that's written in C that controls the Arduino outlet, and also allows it to flash and send data wirelessly to the server. You can see it on the screen over there. Next, we'll go to the code that controls the Android app. The code was written in Java, as you see very soon, and this and the main code that controls the main screen of the app can be shown here. You can see the code that receives data from this server, as well as the code that controls the real-time graph that I mentioned earlier.